to introduce good. I'm really excited today to introduce Nelson Max, who's a professor of computer science at UC Davis. His research areas include computer animation and scientific illustration and visualization. His groundbreaking work in photorealistic computer rendering includes a pioneering use of ray tracing to render one of the first computer generated water animations called Carla's Island. And his award-winning films from the 1970s animating space-filling curves and sphere eversion really set the standard for computer-generated mathematical illustration. So I'm really, really thrilled to have the honor to introduce Nelson Max.
Okay, well, I guess I should be showing up on the screen. There we are in speaker view. And my foray into computer graphics really started when I was a graduate student at Harvard, and Tom Banchoff was a visiting lecturer there, I think in 1964. And as part of his classes, he showed us illustrations that Tony Phillips had made of the sphere version, which turns a sphere inside out by a regular homotopy. And these were like just sketches, which were later cleaned up by the Scientific American artists when his uh, uh, article on turning a sphere inside out appeared in 1966 in Scientific American. But even then, they were just discrete stages of the immersion of the sphere. And they were sliced up into ribbons so you could see inside, but it was really hard to follow the eversion. So eventually I decided it would be nice to make a computer animated version of some sphere eversion so people could visualize it more easily. And I think in 1968 or 69, I applied to the National Science Foundation to do this. And of course, this was very early in the field of computer graphics, and I, in fact, didn't even know anything about computer graphics. I thought it might be possible. And the National Science Foundation had this scheme where this was just a preliminary proposal, and they could give me advice, and they said, go learn more about filmmaking and computer animation. And so I spent the summer of 1969 traveling around the country. I visited Steve Coons and Rod Ruggiero, who had a flight simulator that used computer graphics. And I also visited Education Development Center, which had made these PSSC films. And they basically ghost wrote my proposal for me with all the proper language, and they suggested for the same amount of effort on the part of the National Science Foundation, they could make a bigger grant for 4 films instead of one on turning a sphere inside out. And I also went to MIT Lincoln Laboratory, and I met Bob Davis, who taught me some computer graphics, and I actually made a little bit of animation there that I included in the proposal, and I made some clay animations of the sphere version. I eventually got the grant. I connected in with Bernard Morin, who had a more easily visualized simulation, which he tried to describe to me in words. Um, he's a blind French mathematician, and I don't know, maybe blindness helped him see the hidden parts of the surface. But anyway, this turning a sphere inside out was very surprising because of the Whitney-Graustein theorem, which basically says that two regular curves in the plane are regularly homotopic if and only if they have the same winding number, and an inside-out circle has a winding number -1 instead of the +1 for a regular circle. So you can't turn a circle inside out. So Steve Smale's um, thesis advisor, Raoul Bott, was very surprised by the fact you could turn a sphere inside out. From Steve Smale's theorem, it was really hard to visualize it. And so later, Arnold Shapiro and then Bernard Morin and various other people, Bill Thurston, have multiple ways of turning a sphere inside out. So what I'm going to show you is excerpts of 3 of the 4 films that I made in this Topology Films project. And actually the first one is one of two films on the Whitney-Graustein theorem, the if and only if part of two regular curves in the plane can be turned in, can have a regular homotopy between them if and only if they have the same winding number. And the only if part is what shows you can't turn a circle inside out. And that was one of the four films, actually the two parts were two films that I proposed to the National Science Foundation. And basically, the way this film I'm going to show you on half of the Whitney-Graustein theorem was made is I just made this storyboard and I connected with two undergraduates at MIT who were interested in using with some sort of very old DEC computer that had a CRT screen on it, and Paul Pangaro and Emile Millet, actually created this film just from my storyboard. So my only participation in the film was to create the storyboard. And I don't know, we had a steering committee. Some of the ideas on the storyboard came from the steering committee too. But I'm going to now show you the film as soon as I do my screen share. And let's see, let us share my whole desktop. And here is the film.
You can think of a curve as the path of a moving point, but we require that our curve satisfy certain conditions. First, we only consider closed curves, that is, curves where the moving point returns to the starting position. Second, the point must not jump. It must move continuously. Third, there must be a tangent line at every point on the curve. The tangent vector is defined as the arrow along this line in the direction the point is moving. The fourth condition is that the tangent vector must turn smoothly and continuously as the point moves along the curve. This means that corners are not allowed because the tangent vector would jump. Fifth and finally, we must also require that the tangent vector returns to its initial direction. This prohibits corners at the starting point. Curves which satisfy all these conditions are called regular closed curves, or simply regular curves. A deformation from one regular curve to another consists of a series of intermediate curves, one for each instant of time. As with the curves, we put certain conditions on these deformations. An easy way to illustrate these conditions is to show ways in which they are violated by deforming a figure 8 to a circle. First, you must not break the curve. Second, you are not allowed to lift the curve out of the plane. Every intermediate curve must stay in the plane. Third, the curve may not suddenly jump from one position to another. It must move continuously throughout the deformation. Fourth, corners are not allowed because each intermediate curve must be regular. Cusps are prohibited for the same reason. Fifth and finally, the tangent vector must turn continuously during the deformation. That is, the tangent vector at a particular point must not jump. Here, though each intermediate curve is regular, the tangent vector at the top jumps when the smaller loop disappears. We can also state the conditions for a regular homotopy in a positive way. Each intermediate curve must be regular. That is, if a point moves around the intermediate curve, both the point and its tangent vector must move continuously and return to their initial positions. Also, if we choose a particular point on the initial curve and follow it as the curve deforms, both the point and its tangent vector must move continuously. A deformation which satisfies all these conditions is called a regular homotopy. If there is a regular homotopy between two curves, we say that they are regularly homotopic. Are the figure 8 and the circle regularly homotopic? The ways we have seen for turning a figure 8 into a circle all violate the rules. Later in the film, we will prove that there is no regular homotopy between them. This proof uses rotation numbers. The rotation number of a regular curve is the number of times the tangent vector rotates going once around the curve. For example, this curve has rotation number 1. Remember that a curve is the path of a moving point. You must specify the direction it is traced, and this may affect the rotation number. So a circle drawn in a counterclockwise direction has rotation number 1. But in a clockwise circle, the tangent vector turns in the opposite direction. So the rotation number is -1. This curve has rotation number 2. What is the rotation number of this curve? It is 3. Note that the rotation number is always an integer, since the tangent vector always returns to its initial direction. What is the rotation number of a figure 8? It is 0. Now we will prove this theorem. Two regular curves in the plane which are regularly homotopic must have the same rotation number. If this theorem is true, then there is no regular homotopy between the circle and the figure 8, because they have different rotation numbers. Suppose we have a regular homotopy between two curves. This means that small steps in the deformation will give small changes in corresponding tangent vectors. In fact, the change can be made so small that the tangent vectors stay close all the way around the curves. So the rotation numbers are close. But at the end of the curve, both rotation numbers must be integers, and the only way integers can be close is to be equal. So, the rotation numbers of these two regular curves are equal. In a regular homotopy, we can find a series of intermediate curves so that corresponding tangent vectors stay close from one curve to the next. Therefore, the rotation number stays the same from one curve to the next. So the beginning and final curves same rotation number. This completes the proof. We have used the fact that in a regular homotopy, the tangent vector at a particular point moves continuously during the deformation. This is the condition which enables us to find small steps where the tangent vectors are close. It is not enough that the curves themselves are close. The direction of corresponding tangent vectors must also be close, or nearby curves need not have the same rotation number. As we said before, this theorem shows that a circle and a figure 8 are not regularly homotopic. We can also use it to show that a circle cannot be turned inside out. Suppose we have a counterclockwise circle, which has rotation number 1. Note that the outside is red. If we break the circle, which is not allowed in a regular homotopy, we can turn it inside out. Note that the red is now on the inside, and the circle is traced in a clockwise direction. It has rotation number -1. The theorem tells us that the two curves cannot be regularly homotopic because they have different rotation numbers. So any attempt to turn a circle inside out will violate one of the conditions for a regular homotopy. For instance, this deformation has cusps.
Okay, so I think that's enough for this one. Now let me show the next video, which is actually the second half of the video on turning a sphere inside out. So you'll start with a red surface and eventually see a blue surface. And this is basically Bernard Morin's sphere eversion. This is the second half of this film because the first half talks about the mathematical context of regular homotopy and has some of these models of Charles Pugh that I used to measure the positions of the sphere that he actually created based on my storyboard for this film. So here goes the sphere eversion. Basically, the analogous rules for a regular homotopy: no holes in the surface, no creases. It's got to move continuously with continuously changing tangent planes instead of tangent vectors. So now you see the blue back of the surface poking through. Now here's sort of an isthmus crossing where you had surfaces crossing each other. Here's a triple point, here's a triple point, and in the middle stage we have a quadruple point here. And then it proceeds the same way, actually, and also we have another one of these isthmus and things where two saddle points cross. And now it unwinds, the reverse of what we've seen, and eventually this these two triple points will disappear right now, and then this red part will come down and we'll have the surface blue, so the sphere has turned inside out. So there are several different views of this. Here's a more diagonal view. And this is the region where these two surfaces cross. That's a non-generic point. Creating two more triple points right here is a non-generic situation. And there we have a top view where you can appreciate the twofold rotational symmetry around what was a vertical axis in the original view. So now we have fourfold symmetry if you neglect colors. So you can see the rest of it. I just had the same geometry but switched the colors. So here's a cross section showing the creation of first the blue surface penetrating so it's visible on the outside, and then a deformation which creates the triple points here as these three surfaces come together. And here's the second triple point. So here are some more nicely shaded models or images created by Jim Blinn using Ed Catmull's surface bicubic patch software. Here's the fourfold symmetrical gaze. And here I tried to be able to see inside by breaking the surface up into smaller triangles so you can sort of visualize what's going on as the surfaces. You can see multiple levels of the surfaces here. You see that it's really a regular homotopy even on the hidden parts. I don't think we have to see the rest of this. So another film that we had was Space Filling Curves, and here is one of the space filling curves. You can see this starts 17 minutes through the film where the idea of what is a continuous curve is discussed first. And this is a continuous curve, one of a couple examples in the film that fills up a square.
Earth which covers a square. Here is one given in 1912 by the Polish mathematician Václav Sierpiński. It's my favorite.
So what we see is a sequence of positions moving to a limit curve, which is the Sierpiński curve.
Let's look at this again more carefully to see how the approximations are defined. The first approximation is a tilted square. The sides move out to form this octagon, the second approximation. Square projections form on the slanted sides of the octagon to make this cross-like shape as the third approximation. The motion from one approximation to the next follows a pattern. Whenever a square projection appears, it is pushed to an octagonal shape. And a shape like this is pushed to a new square projection. Here's the rest of the curve. To get the next approximation, each square shape is pushed again to an octagon. And shapes like this are pushed again to square projections. Here's the rest of the curve. The same process repeats over and over. Watch this point move. It approaches a limit. Here are some more points. It can be proved that every point approaches a limit, and that the limit points fit together to form a continuous curve. Thus, the two conditions are satisfied, and the approximations define a limit curve. Here are even more points. The limit points are well scattered on the square. In fact, every point in the square is on the limit curve. One proof of this, which we will not give here, is based on the fact that segments on the first approximation will move to fill up triangles. Note that 4 points come together at the center, and that each side of a triangle is covered twice, once by each color. We will close the film by looking at the approximation process again on graph paper. Start to enlarge the picture so you can see that none of the approximations we credit those who helped make this film, we will stop in there.
Okay, so that's enough for this one. Now, these films were done in the early 1970s. Now I want to switch to a new program I wrote in the past 3 years that is an interactive program. It's available on this website. I'll put this information in the chat. And basically, if I type numbers, I can get a dodecagon, hexagon, and a quadrilateral, say. These angles add up to less than 180 degrees. So if I say I'm done typing, it will bend them. So now I have a 3D shape here. And I can continue. We're basically creating regular tilings of either the sphere, the plane, or the hyperbolic plane. So this, because the angles add up to less than 180 degrees, will be an Archimedean solid. Here's the rest of it, and actually I can puff it out to make a sphere here. So it's a regular tiling of the sphere in the sense that each vertex looks like every other vertex in the arrangement of polygons around it. So the user specifies an initial collection of polygons, and the program tries to create a tiling from it. And it checks a transitivity condition that there's actually a symmetry of the whole tiling that takes every vertex to every other vertex. So if I start over, but type 1264, there the tiling angles add up to 360 degrees, and so if we continue it, we can get a tiling of the plane. And actually I can zoom out, and then you can see it continues to create more and more parts of the tiling by just circling around what it's already created. And in some cases, there may be backtracking required in order to create the tiling. I think this is going to stop soon, but we don't have to see the end of it. If I do, say, 1464, the angles add up to more than 180 degrees, so it's tiling, 360 degrees, so it's a tiling of the hyperbolic plane, and I can continue creating more tiles this way. It actually slows down as I get more and more polygons because it's trying to check the transitivity condition all the time. One thing I can do with a hyperbolic tiling is I can move it, and as I do, more tiles are created in the gaps that the motion creates on the side, so that you get what looks like part of an infinite tiling. So I have a document describing this, and what I'm going to do is copy this part, not only the title of the web page, but eventually I'll also copy the location of this article describing the method of creating the tiling. So I first copied that page, so let me make this smaller. How can I do that? I can't even see. Okay, I'm going to stop screen sharing just so I can do this copying better. So now I have my, where is chat? and I want to go to everyone. Oh no, isn't there a to everyone? Hosts and panelists. I hope that's everyone. This is the website plus some instructions for how to access it. I mean, for how to use it. But I can't see the bottom of this. How can I scroll down to the bottom of my message so I can send it? Well, if you want this DOI, it's here for the article. But I'm basically done. Maybe if I get out of this, I can have a better hope of sending this chat message. Basically, I have a scrolling problem here. Is this going to send it? Save chat? Is that going to send it? In any case, you can probably see the website at the top of one of the pages. So this is it for my talk.
Thank you so much.
Thank you. I didn't receive your chat, but we do have the website in the chat now, so everyone should be able to see that.
Okay, thank you. The chat also has. I don't know why it's not letting me. Let me go away from this chat and try once more and see if I can. No, it's still not showing me the bottom in order to send it. But anyway, thank you for.
Enter it might. I don't know.
Just say enter. Okay, let me try enter. There we go. Thank you.
Okay, I think
that seems to have worked. Yes.
Yeah.
Okay, well that's it. Sorry for running a minute over.
No worries.
And also
copied and pasted and sent so it was everyone. Great. I was going to ask if folks had any questions. I wanted to thank you so much for your talk. That was amazing. I really love seeing those videos. There's people talking about it on the Discord channel, and someone did ask if you'd be able to share a link to all of the videos as well that you shared with us at some point.
Let's see if I can still find them. Let's see. So what I have to do is I have to, let me make this less than full screen. I just made it go away, but let me find my browser and let me go to each of these links. Here's one of them. And now I want to make this big enough, but not too big. And here's one of the links. No, I didn't get it. Well, let me.
We could also do other questions for now and then collect those from you and post them on the Discord after.
Well, here's one. I did get it.
Great.
Okay, so you can ask questions, and I'll try and multi-process to copy the other two links, although I won't, I'm not good at multi-processing, but we'll see if I can do it.
Do we have any other questions? Terrific. Well, I wanted to thank Nelson Max again for an awesome talk and some great videos. And I want to direct folks to the Discord to continue chatting. I know there's some folks. Our No Sherry Todd just posted on the Discord that the film on the rotation number is perfect and that it would deserve to be better known. Which I think I agree. It's wonderful to see. So I think I'll hand the floor back to Aaron one more time to close us out.
Okay, well, thanks, Gabe. Thanks again to all of our speakers for once again lovely presentations. On a personal note, as a youngster, some of my first exposure to the world of illustrating math came in the form of some of Nelson Max's early videos. In particular, I've seen that video on space filling curves decades ago, but never met you until today. So it's delightful to be able to see it again in your presence and with your narration and your story. So thank you very much. Thanks to everyone for coming. Hope to see you next time. Again, if you would like to present in the show and ask format, please let us know. We'd be happy to have you present. And otherwise, see everybody over on the Discord, and see you next time.
Okay, I have one final request. I'm pretty sure you can edit the recording to remove my fumbling about getting the sound to work, so that it'll just, when I try to start the film, let me start it correctly with the right film and the right audio connections.
Sure, I'll do my best to edit that.
Okay, so I guess I need to find the Discord and join. I'm not much of a Discord user, but I'll try.